All right, let me ask you something. When you think of concrete, what comes to mind? Strength, right? I mean, this is the stuff we trust with everything. Bridges, highways, skyscrapers, your house, the ground you walk on every single day. It looks solid. It feels permanent. Like once it's there, that's it. Nothing's moving it. You could hit it with a hammer and the hammer might lose. You could park a truck on it, no problem. Stack an entire building on top of it, still fine. So yeah, concrete has this reputation. Strong, tough, unbreakable. But here's the thing nobody really tells you. Concrete isn't as strong as you think. In fact, it has a weakness, a really simple one, and once you see it, you can't unsee it. And it's not earthquakes, it's not heavy weight, it's not even time. It's something much more basic than that. Let me show you what I mean. Think about this. Have you ever seen a crack in a wall? Not a huge one, just a small line, maybe above a window, along a ceiling, or running down a concrete surface. At first, you don't really think much of it. It just looks like wear and tear. Normal, right? But what if I told you that tiny crack is actually exposing the biggest weakness of concrete? Yeah, that little line is the clue. Because concrete, for all its strength, doesn't fail the way you expect. It doesn't slowly get crushed. It doesn't just give up under weight. Most of the time, it fails in a completely different way. And the scary part? The thing that causes it isn't rare. It's not some extreme condition. It's happening all the time, everywhere, in ways you don't even notice. Wind, temperature changes, the ground moving just a tiny bit, even water. All of these things are constantly acting on buildings, pushing and pulling in different directions. And that's where the problem starts. Because concrete is really good at one thing, but surprisingly bad at another. And that bad at part, that's what brings buildings down. Now don't get me wrong, concrete is still one of the most important materials ever invented. We wouldn't have modern cities without it. But the way most people think about it is kind of wrong. We imagine it as this indestructible block, like a rock, like something that can handle anything you throw at it. But real life doesn't work like that. In real life, materials don't just deal with force, they deal with different types of force. And concrete, it's a bit picky. It can handle being squeezed all day long, but the moment you try something else, that's when things get interesting. Let me put it this way. If you take a solid piece of concrete and press down on it, it'll fight back, hard. But if you try to pull it apart, that's a completely different story. And most people never think about that. Because we don't see buildings being pulled, right? We see weight, gravity, things going down. But behind the scenes, there's a lot more going on. Structures are constantly under stress, not just from above, but from all directions. And sometimes, those forces don't push, they pull. And that's exactly where concrete starts to struggle. So the next time you walk past the building, or stand on a concrete floor, or even just notice a small crack in a wall, just remember this. That crack didn't happen because the concrete was too weak to hold weight. It happened because something pulled on it. Just a little, but enough. And once that happens, everything changes. So yeah, concrete is strong, just not in the way you think. And in the next part, I'm going to show you exactly what concrete is actually good at and why we still use it everywhere, even with this huge weakness. So now that we've kind of broken the illusion, let's rebuild it the right way. Because here's the truth. Concrete is strong, like ridiculously strong, just not in every way. And once you understand what it's actually good at, everything starts to make a lot more sense. So let's talk about that. Concrete has one job that it absolutely dominates at, being compressed. In simple terms, being pushed down. That's where it shines. That's where it's almost unbeatable. Think about it like this. Imagine you put a concrete block on the ground and then start stacking weight on top of it. A person, then another, then maybe a car, then a truck. The concrete doesn't panic, it doesn't bend, it doesn't really care. It just sits there and takes it. You can keep adding weight, and as long as it's within its limits, it'll hold. That's why we use it for things like foundations, columns, and floors, all the parts of a building that are constantly carrying weight from above. Gravity is always pushing down, right? And concrete is basically designed for that exact situation. It's like it was built to say, go ahead, push harder. Now compare that to something like wood. Wood can be strong, sure, but under heavy compression, it can bend, warp, or even crush. Steel? Steel is strong too, but it behaves differently. It can bend before it breaks. Concrete? Concrete doesn't really bend. It just resists hard. And that's actually a huge advantage because in buildings, you don't want things constantly flexing under weight. You want stability. You want something that just holds its shape and doesn't move. And that's exactly what concrete gives you. Let me give you a simple mental picture. Think of a stack of books. If you press straight down on them, they stay in place. Everything is stable. That's compression. Now imagine a skyscraper. All that weight, floors, walls, furniture, people, is being transferred downward, layer by layer, all the way to the ground. And what's handling most of that? Concrete. Columns made of concrete, foundations made of concrete, slabs made of concrete. It's everywhere for a reason, because in that pushing down scenario, concrete is incredibly reliable. Engineers love that. They can calculate it, predict it, trust it. That's why you see massive concrete structures holding insane amounts of weight without any visible struggle. Bridges carrying thousands of cars every day, parking garages packed with vehicles, apartment buildings stacked floor after floor. And most of the time, nothing happens. No drama, no movement, no problem. Because everything is being compressed, and concrete is totally fine with that. Actually, more than fine. It thrives under it. But here's where things get interesting again, because real life isn't just about things being pushed down. Forces don't come in one direction. They come from everywhere. And the moment those forces change direction, even slightly, concrete is no longer in its comfort zone. So yeah, if the world was only about gravity pushing straight down, concrete would be perfect. No weaknesses, no issues. But that's not how buildings live. They deal with wind. They deal with temperature changes, hot days, cold nights. They deal with the ground shifting, even just a little. And all of those things introduce different kinds of forces, not just pushing, but pulling. And that's where this super strong material suddenly starts to struggle. So now you know the first half of the story. Concrete loves compression. It's insanely good at handling weight. That's why it's everywhere. But strength isn't just about how much weight something can hold. It's about how it reacts to all kinds of forces. And in the next part, we're going to flip everything again. Because the exact same material that can hold up a building can also crack way easier than you'd expect if you use it the wrong way.
All right. Now we get to the part that really flips everything. Because up until now, concrete sounds like a hero, right? Super strong, reliable, takes insane amounts of weight without even flinching. But here's the uncomfortable truth. Concrete has a serious weakness. And once you see it, you'll start noticing it everywhere. Concrete is terrible at handling tension. In simple words, it's really bad at being pulled apart. Not a little worse, not slightly weaker, I mean really bad. Let me show you what that actually looks like. Imagine you've got a solid piece of concrete in your hands. Feels heavy, feels strong, almost like a rock. Now instead of pushing down on it, try pulling it from both ends. What happens? It doesn't stretch, it doesn't bend, it doesn't give you any warning. It just cracks. Suddenly. Clean. Done. And that's the key difference. Materials like steel, you pull them, they stretch. You can actually see them deform before they fail. There's a warning. Concrete doesn't do that. Concrete goes from perfectly fine to broken in a split second, and that's what makes it dangerous. Let me give you a simple everyday comparison. Think about a biscuit, or like a dry cookie. You can press down on it gently, it holds. Even a bit of weight, still fine. But the moment you try to bend it, snap. That's concrete. Another one, chalk. You can press it against a surface, no problem. But try to bend it, it breaks almost instantly. That's exactly how concrete behaves under tension. Strong under pressure, weak when pulled. Now here's where it gets interesting. Because most people think buildings fail because they're overloaded, like something was too heavy, too much weight, too much stress from above. But in reality, that's rarely the main problem. Most failures start with tension. Something pulls on the structure, maybe just a little, maybe slowly over time. And concrete doesn't like that at all. Let's say you've got a concrete beam. Looks solid, looks like it can hold anything. Now put weight on top of it. The top part gets compressed, that's fine. But the bottom part, it actually gets pulled. Yeah, pulled. Because the beam is trying to bend even just a tiny bit. Top squeezes, bottom stretches. And that bottom zone, that's where cracks start. You won't see it at first. Maybe just a hairline crack, barely noticeable. But that's all it takes. Because once concrete cracks, it doesn't heal, it doesn't bounce back. That crack is permanent. And over time, it can grow wider, longer, deeper, until one day, it's no longer just a crack, it's a failure. And the crazy part is, all of this can happen under loads that seem totally normal. Nothing extreme, no explosion, no dramatic event. Just everyday forces slowly pulling where concrete can't resist. That's why engineers don't trust concrete on its own when tension is involved, because they know something most people don't. Concrete is strong, but only in one direction. The moment you ask it to do the opposite, it's a completely different material. So next time you see a crack in a wall, a ceiling, or a concrete surface, don't just think cosmetic. That crack is telling you something. It's showing you exactly where the concrete was pulled, where it couldn't cope, where its biggest weakness showed up. And that's the part most people never think about. They see concrete as solid. Engineers see it as limited. And once you understand that limitation, you start to understand why buildings are designed the way they are. Because if we relied on concrete alone, a lot more things would be cracking or worse. And in the next part, we're going to talk about that exact moment, what concrete is really afraid of, and why these tiny forces happening every day are actually a much bigger deal than you think.
So, now you know the weakness. Concrete hates being pulled. Even a little bit of tension can start a crack. But here's the real question. Where does that tension actually come from? Because it's not like someone is out there grabbing buildings and pulling them apart, right? That's the part most people miss. The forces that damage concrete aren't dramatic. They're not obvious. They're small, constant, and honestly, kind of boring. But they're everywhere, and over time, they add up. Let's start with something super simple. Temperature. Yeah, just heat and cold. During the day, concrete heats up and expands. At night, it cools down and shrinks. Sounds harmless, right? But think about it. That expansion and contraction is movement. Tiny movement, sure, but it's happening every single day. Now imagine different parts of a building heating and cooling at different speeds. One side gets more sun, another stays in the shade. One part expands more than the other. That creates stress inside the structure. And stress means tension, pulling, exactly what concrete hates. Now add water into the mix. Water gets into tiny pores and cracks in the concrete. When it freezes, it expands, and not a little, it pushes outward,
from the inside. So now you've got internal forces literally pulling the material apart. Again, not a huge explosion, just small pressure over and over again. But every time it freezes and thaws, it gets worse. Then there's the ground. People think buildings sit on solid, unmoving earth. They don't. The ground shifts, very slightly, but it does. Maybe the soil dries out. Maybe it absorbs water. Maybe traffic nearby causes vibration. Maybe construction next door changes the load. All of that creates movement. And when the foundation moves, even a tiny bit, the structure above has to adjust. That adjustment creates tension. Parts of the building get pulled in different directions. And again, concrete doesn't like that. Then there's wind, not just storms, even normal wind. Tall buildings sway. You might not feel it, but they do. Just a few millimeters sometimes. But that movement creates bending, and bending means one side compresses, the other side gets pulled. There it is again, tension. And here's the crazy part. None of these things are extreme, no disaster, no big event. This is just everyday life for a building. Sunlight, air, water, ground, all slowly pushing and pulling in different ways. And concrete is sitting there dealing with all of it. But remember, it's only really good at one thing, compression. The moment these everyday forces introduce tension, that's when problems start. Small at first, almost invisible. A hairline crack, a tiny separation, something you could easily ignore. But those small cracks, they're not random, they're signals. They're showing you exactly where the material is being pulled, where it's struggling, where it's starting to fail. And once a crack forms, it actually makes everything worse. Because now water can get in easier, temperature changes have more impact, the structure becomes even more vulnerable. So it turns into a cycle. Small tension to small crack to more damage to bigger crack. And it just keeps going. All from forces that seem insignificant. That's why I said earlier, concrete isn't afraid of something dramatic. It's afraid of something simple. Movement. Not weight, not pressure. Movement. Anything that causes it to be pulled even slightly over time. And once you start looking at buildings this way, you realize something important. The real challenge in construction isn't just making things strong, it's controlling movement. Because you can build something that holds massive weight, but if you don't deal with these tiny, constant forces, it won't last. And that's exactly why concrete is almost never used alone, because on its own, it just can't handle the real world. So in the next part, we're going to look at the solution, how engineers take this material with a huge weakness and turned it into something strong enough to hold up entire cities. Now we've got a problem. Concrete is strong under compression, but weak under tension, and real life, full of tension. So how do we fix that? Because clearly we still use concrete everywhere. Bridges, buildings, roads. It's not like engineers just said, yeah, this material has a huge flaw, let's use it anyway. No, they solved it. And the solution is actually pretty simple. They gave concrete a partner, steel. That's it. That's the whole trick. Now, on its own, steel behaves almost the opposite of concrete. Steel is great under tension. You can pull it, stretch it. It doesn't just snap. It bends. It gives you warning. It holds together. So now, imagine combining the two. Concrete plus steel. One handles compression. The other handles tension. Suddenly, you've got something way more powerful than either one alone. This is what we call reinforced concrete. And honestly, this is what makes modern construction possible. Let me break it down in a simple way. Picture a concrete beam again. You put weight on top, the top gets compressed. Concrete is happy. But the bottom, that's where tension happens. That's where cracks would normally form. So what do engineers do? They place steel bars inside the concrete, right in that tension zone. Now, when the beam tries to bend, The concrete still handles the compression at the top, but the steel at the bottom takes the tension. It's like backup, like reinforcement, like giving concrete exactly what it's missing. And here's the genius part. Concrete and steel actually work really well together. They expand and contract at almost the same rate with temperature. So when it gets hot or cold, they move together, not against each other. That's super important, because if they move differently, the whole thing would fall apart. Also, concrete naturally grips onto steel really tightly, so the steel doesn't just sit there loose, it's locked in. When forces act on the structure, both materials respond together, like a team. Let me give you a simple analogy. Think of concrete as something strong but brittle, like a shell, and steel as something flexible and tough, like muscle. On their own, limited. Together, way more capable. Concrete keeps everything rigid and stable. Steel keeps everything from tearing apart. Now go back to that crack problem we talked about. Without steel, once tension appears, crack, game over. But with steel inside, the crack might still start, but it won't spread the same way, because the steel is holding everything together. It's carrying that pulling force. It's stopping the failure from getting worse. That's why reinforced concrete doesn't just suddenly collapse. It gives time, it gives warning, it controls damage. And that's exactly what engineers want. Not perfection, control. Because in the real world, you can't eliminate forces. You can't stop temperature changes. You can't stop the ground from moving. But you can design structures that handle those forces, that adapt, that survive. And that's what steel plus concrete does. It turns a flawed material into one of the most reliable systems we have. So next time you see a concrete structure, a bridge, a wall, a building, just remember, there's probably steel hidden inside it, doing the work you can't see, handling the forces you don't notice, making sure that when the world starts pushing and pulling, the structure doesn't fall apart. And in the final part, we're going to connect all of this to real life, what cracks actually mean, when you should worry, and why some failures still happen even with all this engineering. All right, so now you understand the full picture. Concrete is strong in compression, weak in tension. Steel comes in to fix that. On paper, problem solved. So here's the obvious question. If we already know all this, why do we still see cracks everywhere? Why do buildings still fail? Why do bridges still collapse? Because here's the part most people don't realize. Engineering doesn't eliminate problems, it manages them. And sometimes, things still go wrong. Let's go back to something simple. A crack in a wall. You've probably seen it before, maybe in your apartment, maybe in a stairwell, maybe in a parking garage. Thin line, doesn't look serious, so most people ignore it. Just cosmetic, normal. And yeah, sometimes it is, but sometimes it's the first warning sign. Because remember what a crack actually means. It means tension happened. It means the concrete was pulled beyond what it could handle. Now, that doesn't automatically mean danger. Buildings are designed to crack in controlled ways. That might sound weird, but it's true. Engineers expect small cracks. They plan for them, because it's better for a structure to crack slightly than to fail suddenly. So not every crack is a problem, but the pattern matters, the location matters, the size matters. Let me give you a few examples. A tiny hairline crack in plaster? Usually nothing. A long diagonal crack running across a wall? That could mean movement in the structure. Cracks near windows and doors? Common. Those are weak points. But if those cracks keep growing, that's when you pay attention. Because cracks don't just appear randomly. They follow forces. They tell a story. Where the structure is being stressed, where it's moving, where something isn't behaving as expected. And here's where things can escalate. Because once a crack forms, it creates a pathway. Water gets in, air gets in, and more importantly, Moisture reaches the steel inside. Now remember that steel we talked about? The thing that makes everything work? It has its own weakness: rust. When steel starts to corrode, it expands, and when it expands, it pushes outward on the concrete around it from the inside. So now, instead of just dealing with external forces, the structure is attacking itself internally. More pressure, more cracking, more damage, and it becomes a chain reaction. Small crack, water gets in, water, steel rusts, rust expands, expansion, bigger cracks. And over time, that can turn into serious structural damage. Now add in real-world factors. Maybe the building wasn't constructed perfectly. Maybe the materials weren't as good as they should be. Maybe maintenance was ignored. Or maybe the environment is just harsh. Lots of rain, freezing temperatures, coastal air. All of these things make that process faster. And sometimes, that's when failures happen. Not because engineers didn't understand concrete, not because the idea was wrong, but because in the real world, small problems add up, slowly, quietly, until one day, something gives. And yeah, in extreme cases, that can lead to collapse. But here's the important part. Most failures don't come out of nowhere. There are signs: cracks getting bigger, surfaces flaking off, rust stains, unusual movement. The structure is basically telling you something's not right. The problem is, most people don't know how to read those signs. They just see a crack and think it's nothing, or they panic over something that isn't serious. So let's bring it all together. Concrete isn't unbreakable. It's strong, but only in the right conditions. It hates being pulled, and the real world is full of forces that pull, so we add steel to help it. That makes it incredibly reliable, but not invincible. Because over time, movement, water, temperature, and neglect can still break the system down. And when that happens, it usually starts small. A crack, just a line, easy to ignore. But now you know better. That crack, it's not just a crack, it's a message. And if you understand what it's telling you, you understand how buildings really work. Not as solid, unchanging objects, but as systems constantly dealing with forces, adapting, and sometimes struggling. And that's the part nobody tells you. Until now.